Hello and good morning to everyone. So our today's lead code question is 3661, that is maximum wall destroyed by robots. So basically this is a very nice question. So in this question we are given three arrays: robot array, distance array and walls array. So robot array will tell us the position of each robot. Distance array tells us the maximum distance that the ith robot bullet can travel, right? And walls array tells the position of each wall, right? So each robot has one bullet, right? And it can either fire it to the right direction or to the left direction, right? At most distance of I meters, right? And a bullet destroys every wall in its path that lies within its range. So suppose there is a robot here and its range is from this point to this point, like this is distance and this is distance, and this is a position of the robot. So this so suppose the robot fires the bullet in this direction, so that bullet will destroy all the walls present in this range, right? And if it fires in this direction, then it destroys all the walls present in this direction, right? And these robots are fixed obstacles, right? They are fixed. So one more condition is there: if a bullet hits another robot before reaching a wall, it immediately stops at that robot. Now suppose there is one more robot here. So earlier the bullet can go from this position to X, but now once the bullet hits the robot, it will not go ahead, it will stop there only, right? So what we have to do is we have to return the maximum number of unique walls that we can destroy, right? That the robots can destroy. So we have to return the total number of unique walls that the robots can destroy. And a wall and a robot may share the same position, like suppose this is our index, so here a wall can also be present and a robot can be present, and the wall can be destroyed by the robot, right? At that position, like whichever robot present here, the wall will be destroyed by that robot. And robots are not destroyed by bullets, right? They are not destroyed. So let's see the first example to get it more clearly. So we have one wall at index 1, another wall at index number 10, and we have a robot at index number 4, and it can shoot at a distance of 3. So what is the range of this robot? So the range is 4 minus 3 and 4 plus 3, that is it can shoot to 1 to 7. So in this range, if it shoots left, then it can kill, it can destroy one wall. If it shoots right, then it can shoot up to 7, so it destroy 0 wall. So we'll take maximum, that is 1, so it shoots left and the answer is 1. So let's see the next example. So in the next example we have two robots and three walls, and the walls are present at 2, 5 and 7, like these are the three walls present. And we have two robots, one robot is at 2, here we have one robot having distance 1, and the another robot is at 10, one more robot at 10 with range 5. So let's see the first robot. So this first robot is at 2 and its range is 1, so it can kill from 1 to 3, but on its left there is no wall. On its right it can kill up to 3, so here also no wall, so it can kill only this wall. So robot 1 will kill only one wall. Let's see the next robot. Next robot is at 10, so it can kill from 5 to 15, right? As the distance is 5, so if it shoots left, then it will kill two walls, that is 5 and 7. If it shoots right, there is no wall. So the total number of walls that these two both robots can kill are: this can kill one wall, this can destroy two walls, so total three walls that they can destroy. So the answer is 3. So let's see the next example. In next example, a wall is present at 10, right? And we have a robot at 1, and at we have another robot at 2. This robot has a distance of 100, this robot has a distance of 1. So see the range of this robot. The range is 1 minus 100, 1 plus 100, but in the right side we have another robot at 2. So though it has range up to 101, its bullet cannot pass this robot. So its right range will not be 101, it will be 2, right? So the range of this robot is minus 99 to 2. There is no wall in that range, right? Let's see the second robot. Second robot range is 2 minus 1 1 and 3. There is no wall in that range also. So the number of walls they destroy is 0. But the main point here too is to explain this concept that though its range is 101, but the right range has become 2 as there was a robot present. So let's see the constraints. So the total number of robots can be up to 10 ki power 5, and the total number of walls can also be up to 10 ki power 5, and each robot and wall index can be position can be up to 10 ki power 9 on the number line, right? And the distance of I can be up to 10 ki power 5, and it is given that all the robots are unique, means at each position only one robot will be present, and all even the same thing, all the walls are also unique. So let's see the approach step by step. So first of all, what we have robots and we have walls, but they are not arranged properly on the number line. So what we do is, first of all, we will sort all the walls and all the robots and distance, so that we arrange all the walls and all the robots on the number line properly, right? So after sorting, what we have now robots and the walls arranged properly on the number line, right? So next it is given that the bullet either stops if it reaches the maximum distance, that is distance of I. Either it reaches the maximum distance, or if there is some robot present to it, right? So the bullet either stops when it reaches its maximum range, or if some robot is present in between, right? So for every robot, what we do is we'll be finding its range, that is left and right, what you call right coordinate up to which its bullet can travel. So let's see what its left can be and what its right can be. Now suppose our robot is present at position, and its range is distance. So normally if we assume that there is no robot in between. So what its left range will be position minus distance, and its right range will be position plus distance, right? Position minus distance is left one and this is right one. But suppose if some robot r dash is present, then what is the left? So whichever is maximum out of this, either maximum of this, that will be the range of this. So left range of this robot r is position minus maximum of position minus distance, or left robot plus 1, left robot plus 1, right? And similarly the right range is whichever, suppose r dash is present here, so minimum of these two, minimum of position plus distance or right robot position minus 1. So after we get the, so with this we get the range left and right, we get the range of this robot r in which it can hit a bullet, right? So we get the range. Now, so if some other robot also present, overlapping can occur between adjacent robots only, right? So this is one observation. See, uh, as we know, a bullet cannot pass a robot. So if some robot is present here, and it shoots in the right direction, so the bullet of this robot does not pass this robot r dash. So if there is, suppose it shoots in the right direction and it shoots in the left direction, so even if collision occur, it occurs in the adjacent pair of robots only, right? Occurs in the adjacent pair of robots only. That means, what does that mean? That means robot I depends on robot its previous robot only, that is robot I minus 1, if collision occurs, right? It doesn't depend on all the robots, right? Its answer doesn't depend on the all the robots, its answer depends on only on the previous robot. So if we have seen the problem properly, we have a sequence of robots, and this ith robot depends on the I minus 1th robot, that is dependency is there, and we have to maximize the number of walls. So all these three things points towards a dynamic programming DP solution, right? So we have declared our DP states. So we have two direction, left direction and we have right direction. So dp of I and j, what it will store, it will store the maximum number of walls that has been destroyed till robot number I, if ith robot shoots in the left direction, right? What it does is stores the maximum number of walls that is destroyed till robot I, if the ith robot shoots in the left direction. Similarly dp of I will I and 1 will store the maximum number of walls if I shoots in the right direction. So these are two DP states, are two DP states, right? So let's see the base case. Base case is like for robot number 1, right? First robot, that is I is equal to 0. So its left is dp of 0 comma 0, that is walls, all the walls present in the left range. Like this is the first robot, this is the first robot, so there will be no robot in its left. So whichever walls present in its left range, that will be the dp of 0 comma 0, right? And then if you'll see in the right direction, so in right direction there are two possibilities: either there is no overlapping or overlapping is there. So we have to see, right, which one we will be taking, right? So this is for base case. Then transition for each robot I, like dp state transitions, right? So what we do is, next we start processing from left to right, each robot one by one, right? We'll process each robot one by one. So let's see the three different cases that we can face. So the first case is robot I, ith robot shoots in the right direction, right? This is a robot and it shoots in the right direction. And already we have find the that what you called, already we have find for the previous robot. For previous robot we have answer of its left shooting, answer of its right shooting, right? How many walls has been destroyed till I minus one robot. So for this current robot R, what we do is, it is shooting in the right direction. So there is no collision between this ith robot and I minus one robot. So what it does, we does is, we take maximum of answer of the I minus one robot, that is left direction and right direction. We take maximum of that, and then add the number of walls in the right range, add the number of walls in the right range of the current robot, right? Number of walls in the right range of the current robot, and that is the answer for the right direction. That is the answer, or that is the number of walls destroyed by the ith robot in its right direction, right? So as the right shooting goes in the forward direction, so no overlapping with the previous, so we take the best of the previous. And next robot we haven't considered yet, right? That's why we are not considering overlapping with the next robot. So this is a case 1. So let's move to the case number 2. Case number 2 is the ith robot shoots in the left direction. Now there are two possibilities is like the I minus 1th robot. I minus 1th robot also shoots in the left direction. So if both shoots in the left direction, then this bullet at max can go up to I minus 1. So there is no overlapping again, right? So in that case, in this case, the left value is its left answer is dp of I minus 1 0, and whatever walls present in this range, whatever walls present in the range of the ith ith robot, right, that will add. So that will be storing if both shoots left direction, right? But the second case is, this ith robot shoots left direction and I minus 1th robot shoots in right direction. Now overlapping can happen, right? Now overlapping can happen. So what we do is, we'll take the result of right direction of I minus 1, result of right minus number of walls destroyed by I up to I minus 1 robot. If it shoots in right direction, then the current number of left walls, like how many left walls the current robot can destroy, that will take, and then we subtract the overlapping walls, right? How many walls are overlapping. Now how to find the overlapping range, like how much range, how, what is the range of the overlapping range of I minus 1th robot and ith robot, how we will finding that. So suppose this is range of ith robot and this is range of I minus 1th robot. So if you'll see what is the overlapping range, left of ith robot and right of I minus 1th robot. So the overlapping range is current left start, that is left of current robot and previous of right robot, right? So we get the overlapping range, and in this range we will find the number of volts. So if you'll see for case 2, that is firing in the left direction, so we have two cases. So final dp update, that is dp of I and in left direction, what we do is we'll take maximum of both the cases. Case 1 in which both are firing in the left direction, case 2 ith is firing in the left direction, I minus 1 is firing in the right direction. So we take maximum of these two, right? So the next question is how to find the number of volts in the range. Suppose we have now we have a sorted array volts, and we have a range that is from L to R, and we have to find the number of volts in this range. So how to do that? So for that we will be using binary search, right? So I hope you may know these two functions, lower bound function and upper bound function. Both works in log of n and it works only on sorted arrays, right? So what lower bound of some function L, what it gives, it gives the first index where our value, is greater than or equal to L, right? Greater than or equal to L. So it will give us the first index. Similarly upper bound of R will gives us the first index where our value is greater than R. So to find the number of volts in the range L to R, we need the first wall which is present at L. So lower bound of L will give us the that index, right? And similarly for R, we want the first index where our wall is greater than position R. So that will upper bound will give us. So subtracting both upper bound and lower bound, we get the count of the number of walls present in the range. So let's see example to get it more clearly. So suppose we have walls 2, 5, 8, 10 and 15, and our range is 5 to 10. So lower bound of 5, so it will give us the first index where we get 5, that is index number 1, so we get index 1. Upper bound of 10 will give us a first index where value is greater than 10, so at 15 value is greater than 10, so 0, 1, 2, 3, this is 4. So how many total number of walls, that is 4 minus 1 yani 3, 3 yani 5, 8 and 10. So these are the walls present in the range from 5 to 10. So this way, using lower bound and upper bound, we will be getting our number of walls in that particular range. So let's see an example, right? So we are having robots 2, 6, distance 4, 4, and these are the walls. So first of all, as we already discussed, we will sort robots and walls, right? So see wall 1, then robot at 2, wall at 3, wall at 4, wall at 5, another robot R at 6, wall at 7, and wall at 8. So we have two robots, right? And these different walls, and both robots have a range of 4, 4, right? So we have sorted them, and then we have added a dummy robot at the end, so we do not have to check the edge cases, right? For that we have added a dummy robot at the end, right? So robot zero's position is 2 and distance is 4. So what are its left and right ranges? So its left range is 2 minus 4, that is minus 2, right? So this is left range. What is right range? Right range is 2 plus 4, that is 6, and its position is 2, that means minus 2 its position 2 and its right range is 6, right? And we have another robot at 6, so our bullet won't go at up to 6, so its right range will be 6 minus 1, that is 5. So its range is from minus 2 to 5. And the number of volts in left range, that is minus 2 to 2 is 1, right? Number of volts is 1. And the number of volts from 2 to 5 is 3, that is 3 4 and 5, that is 3 4 and 5. So this is our base case, that is first robot. So dp of 0 comma 0, dp of 0 comma 0 is 0th robot and in left direction, in left direction. And how many volts are there? 1 volt. 0th robot in right direction, how many volts are there? 3 volts. So we have stored these answer in our dp array as the base case. Next we move to robot 1. So robot 1 is at position 6 and its distance is 4. Distance is 4 means this is position 6. 6 minus 4, that is 2. But we have already another robot at 2, so we take 2 plus 1 3. So this is a left range of this first robot, and 6 plus 4 is 10. So we get the right range as 6 to 10. This is the right range 6 to 10. And how many volts are present? 2 volts, that is 7 and 8. And similarly left range is, it's from 2 to 6, but a robot is present at 2, so we have taken 3 because a bullet will not surpass this robot, right? So how many volts are present? 3 volts are present, that are 3 4 and 5. So here 3 volts are present, here 2 volts are present. So let's see the cases one by one. So case 1 is robot shoots, this robot shoots it in the right direction, right? So as we know, the zeroth robot has 1 in the left direction and 3 in the right direction. And now this robot shoots, one robot shoots in the right direction. So what can be the maximum answer for this? Maximum of this plus plus the number of volts in the right direction, that is 3. 3 is the maximum of zeroth robot, and the number of right volts, that is 2, so 5. So if this robot shoots in the right direction, then the total number of volts that can be destroyed till now will be 5, right? This is our one answer. Then if robot this shoots in the left direction, then we know there are two cases. Two cases is like the previous also shoots in the left direction and the current also shoots in the left direction. So if previous shoots in the left direction, it has destroyed 1 volt, and our current left volts are 3, so total is 4. And the other thing is that like current shoots in the left direction, previous shoots in the right direction, that is the overlapping case. So previous right range, that is 2 to 5, and 3 volts are present in that range, right? And current left range is 3 to 6 and volts are 3 4 5. So the overlapping range is from 3 to 5. This is the overlapping range. And how many overlapping volts? 3 overlapping volts, right? So the formula, that is right of previous yani 3, current left is 3 and overlapping is 3, so total 3. So we take maximum of 3 and 4, right? For the left direction we have two cases, so we take maximum of that 4 and 3, and so we store 4 as the answer. So we have processed all the robots. So the final answer is, our last robot was robot number 1. So final answer, maximum of its left or maximum of its right, that is maximum of 4,55. So 5 is the answer. So let's move to the code part. So initially we have taken the size of the robots, and then we have taken vector of array. See, if we have taken vector of vector, that will be slower, because in that the memory allocation is not contiguous, right? So but in vector of array, the memory allocation is contiguous, that makes it faster than vector of vector. That's why we have taken vector of array. And then we have stored all the robots with their respective distances, and then we have sorted the robots with their distances and the volts to properly what we called arrange them on the number line. And then we have added the dummy robot, right? We have added the dummy robot to avoid the binary checks. And now this is our function, this is our helper function. This type of functions are called helper functions. So this is our helper function to find the number of volts in a range L to R. And we already discussed, see, first we find upper bound of R, upper bound of R in the array volts, and lower bound of the uh, range L in the array, and then this gives us the two indexes, right? And then we take the differences of upper bound minus lower bound. This we already discussed in the approach. Then we have declared our DP states. So in DP we have two DP states, that is 0th for the left side and 1th for the right side. So we have declared again vector of array, again the same reason why we have declared this, as it is faster than vector of vector. Then our base case, that dp of 0 comma 0. So this is our first robot, so there is nothing in its left. So what we do is, we'll find the number of this is its position, that is x of 0 comma 0 is the position of this robot. And what will be its left boundary? Left boundary is position minus distance. Position, that is x of 0 0, minus distance, that is, as we are storing robot position and distance in x, x is stored as position and distance, that's why we are doing it. So we get the left value for the robot 0, right? Then we are finding its right side. So in right side there are two possibilities. If another robots are present, then overlapping may happen, so this is one. And if only one robot is there, if only one robot is there, then again, like its position and then position plus distance, right? But if another robot is there, then we have to see which one is the what will be the right range. So suppose if r dash is present here, then position of the next robot, position of the next robot minus 1 minus 1, or position of the current robot plus distance, position of current robot plus distance, we take the minimum of these two, right, as the r value, and l value is the position of the current robot. So this way we get dp of 0 1 also. Then we start from iterating from we start transition for each robot from I is equal to 1 to n, and we see all the three cases that we have already discussed. That is, our current robot shoots in the right direction. Right direction means there is no overlapping. That means we take the maximum of the previous robot, then we take the uh, what we call number of volts from position to position plus right. Or if overlapping is there with some overlapping, no sorry, if some robot r dash is present, then the position of that robot minus 1, or position of current robot plus distance, we take the minimum of this, right? This query function returns as the number of volts in that particular range. So let's see the case 2. Case 2 is shooting left, right? Shooting left with no previous means both shoots in the left direction. Our current shoots in the left direction and previous also shoots in the left direction. So dp of ij is a previous shooting in left direction is this answer, plus the maximum of position of this robot. Position of this robot is x of I minus 1 0 plus 1 robot plus 1, or the this position of this robot minus distance. So we take the maximum of this. This will give us the left value, and the right value will be the position of the robot. Then third case is shoots in the left direction, but previous shoots in the right direction and current shoots in the left direction, means overlapping will be there. So left, we find the left start, we find the left end of the current, and then we find the overlapping range, then the result will be right value of previous, then number of volts in the current, and then the subtracting the overlapping volts, right? And then at the end we'll store the answer of the maximum of this case or this case for the left side of the current robot, right? And at the end we return the this maximum answer of the last robot. So I hope I am able to explain you the whole approach properly. So if you get the solution, please make sure to like, share and subscribe the channel. Thank you.